Now that we've done some work with various ways that we can say things like domain and range about functions, we can combine functions and we can compose functions or put them together, we are going to be looking at how we can transform functions, and more specifically, how certain changes that we make in the graph of a function affect what the equation looks like, or vice versa. If we make changes in the equation, how does that affect the graph? And this is a unique lesson because you should be watching this after you have already done an in-class activity on Desmos, which has given you some of this information. So we're going to summarize today the information that we went over in class. So we have our translations. Okay, these are the first thing that we looked at. So when we have y equals f of x, so y equals f of x, we're going to call all of our functions f for the purposes of this lesson. If we want to translate vertically, okay, so a vertical translation, we would write y equals f of x plus d. So what is a vertical translation? A vertical translation is where you take the graph of your function. So let's say we have the graph of our function here. Let's make a nice parabola. We could translate it vertically if we wanted to move it up. And we do that. We could also possibly move it down. So a vertical translation is keeping the same function, but we are simply sliding it in the coordinate plane up or down by a fixed number. And the d is a fixed number. So when we have y equals f of x plus d, we raise or lower our y values by d. Okay, so if you had like y equals x squared plus 3 is y equals x squared moved up 3 units. So you're sliding the entire graph. You're not changing the shape at all. You're not changing the orientation or the positioning of the graph. You're just sliding it up and down when you're adding a number on the end of the function. That's why we call it y equals f of x plus d. Okay? So, next one. This is our first transformation. So let's call this number 1. This is our vertical translation. We then have a horizontal translation. So that's y equals f of x. And we're going to change y equals f of x to y equals f of bracket x plus c. And I write x plus c. I know in the book sometimes he will use x minus c, but I like you to write x plus c because whatever c is negative, we go right. Whenever c is positive, we go left. Okay? So you have to be a little careful here with this one. So this shifts x values left, which is if c is just positive, if it's actually x plus c, or right. So it works in the opposite of the way our y translations work. So generally, it's a pretty good rule that our y translations and expansions work intuitively, and anything on the x will work counterintuitively. And this has to do with the fact that we've got things operating directly on the x versus with the y, it's actually on the other side of the equation. But that's not really necessary to be able to perform it. So if I have, for example, an absolute value, okay, so I have y equals the absolute value of x, that horizontal translation might look like we're moving it over here or over here. We still haven't actually, and this would be like a minus some number would move it to the right, and a plus some number would move it to the left. And with those translations, here, again, we're not changing the orientation, we're not stretching or shrinking it, we are just moving it from side to side. So acting on the x moves side to side, adding or subtracting to the x, adding or subtracting to the whole function moves it up or down. Our difference here is if we had like y equals x plus 3 and that whole thing squared, this is y equals x squared moved to the left. So plus moves us to the left 3 units. Okay. So those are our two translations that we've looked at. Next, we have our two different reflections. Okay. So we have our first reflection. We're going to do the y first generally because, again, they tend to be more intuitive. So we have y equals f of x, and we change it to y equals negative f of x. So we stick a negative in front of the whole function. That is going to reflect or flip us over the x-axis. And we'll talk a little bit more about combinations of functions in 2.6. So how do we deal with if we have a reflection and a translation, and how does that look, and what order do we do them in? So we'll clarify that as we get a little further in. Okay, so this reflects or flips over the x-axis. So when we have a reflection, sometimes it can get a little confusing because you might be thinking right here. So we're reflecting over the x-axis, and I might say this is a reflection in y. So it is a reflection in the y direction, but it's a reflection over the x-axis. So if you say, oh, it's a reflection in y, I would probably give you credit for that because that generally is describing the transformation. You can also say it's a vertical reflection because you're reflecting vertically. But if you're saying it's a reflection over an axis, it is a reflection over the y-axis. Okay, so let's actually make sure we have a nice title. These are our reflections. We'll just erase that line and put it up a little higher. So our reflections, we have our vertical reflection, which is in the x-axis. We also have our horizontal reflection, which is acting on x. We're doing y equals f of x goes to y equals f of negative x. And this reflects over the y-axis, and that is in the x direction. Okay, so a parabola is actually not a good visual example for this. What we're talking about here is the best one we have is a radical. And the reason the radical is the best is because it's not the same on both sides of the x-axis. So if we reflect that, sorry, on both sides of the y-axis. See, even I get mixed up about these things. So we're reflecting over the y-axis, and so we're going to be pointing that direction. So it flips directly over the y-axis, and we've got a mirror image. Okay, and I'm just going to clarify and summarize down here. So we have y equals negative radical x is a reflection in the y direction, but over the x-axis. So if it's outside the function, this is our outside the function, that's y direction, but x-axis, so it's a vertical reflection over the x-axis. And then if we have y equals radical negative x, that is going to be a reflection in the x direction, but over the y-axis. So we're flipping it horizontally, so our reflection is going to be, but it's going to be flipped over the y-axis. Okay, so that's you're flipping it sideways, but over a vertical axis. The y1, you're flipping it up to down or down to up, but you're flipping it in over the x-axis. So, like I said, even sometimes mixes me up around a little, so make sure that you're really clear about which reflection is reflecting which way. Okay, last one and everybody's least favorite. We have expansions and compressions. So expansions and compressions are really two descriptions, two ways to describe the same thing, depending on what it visually looks like. So this is the only transformation that we do. And technically, it's not even what you would call strictly a transformation, because you're actually taking the graph and you are changing it. You're stretching it or you're squishing it, depending on what number. And this is all done by multiplying by some constant. So we have a vertical expansion or compression. This is our first one, our vertical expansion or compression in the y. Okay. And you're mostly going to be working with vertical expansions and compressions. There are actually not, all of the functions we're working with, you actually could go either way. You could write, if you see that if you have a graph and you see that it's been expanded or compressed, you could write it in x or you could write it in y, and they would both be accurate as long as you've got the scale factor right. But we're going to be really focusing on those y expansions or compressions until we get to trigonometry, where they actually don't do the same thing to the function. So this is the first time we're actually going to change the shape. So we're looking for a vertical expansion or compression. We're looking at y equals f of x. And that is going to y equals some a times f of x. Okay? And it's an expansion if we have a greater than 1. And it's a compression if a is between 0 and 1. Okay? And you might be asking, well, what about if it's less than 0? What about, can't we have a negative scale factor? We can, but that just is the same as an expansion or a compression plus a reflection. So the negative component of any scale factor would actually just be read as a separate transformation, and that would be your reflection piece. So generally, we're looking at the a being the positive part of the number and the negative being associated with the reflection. Okay, so we have here, if we have, say, a lovely parabola, an expansion or a compression could be a stretch here, or it could be something where you're kind of stretching, you're compressing it, or you're pushing it down. So we call this one where you're kind of, where you think about that you're pulling out in the y direction. If you think about it being on a piece of silly putty, you're kind of pulling it out in the y direction. That would be an expansion. And if you're kind of pushing it down, squishing it down, that would be a compression. Okay, expansion in y and a compression in y. And that would be given by that number that's multiplying the whole function. Okay. The scale factor, so this is a vertical expansion or compression. We call a is the scale factor. So what happens is when you're actually trying to calculate it, from your kind of base function, so the original function you started with, like y equals absolute value of x, y equals x squared, y equals radical x, y equals x cubed, any of our kind of function friends, what that means is for the same x value, you would be multiplying the y value of your old function by the scale factor. Okay, so if it's y equals x squared, instead of going 0, 1, 4, you would go 0, 2, 8 if you were counting for x equals 0, 1, and 2. So now we have our second kind, which is a horizontal expansion and compression. And you won't really have to do a whole lot generally with horizontal expansions and compressions until we get to trig. You may, if we're using functions that are not kind of symmetrical, or if you're using some kind of piecewise function that's like a bunch of lines stuck together. So horizontal expansions happen in the opposite way. So if your a is between 0 and 1, it's actually an expansion, and it's a compression if a is greater than 1. So when I think of a horizontal compression, I actually think about you're squishing a function. So this is taking y equals f of x and changing the equation to y equals f of bx. Okay, so we're multiplying what's inside the f by b. Now, what does this look like? So if we have our good friend, the parabola, it's probably the function you're most familiar with that is the least, has enough going on. You can't really use a line because lines are a little bit too simple. Okay, if we want to do a horizontal expansion, it's actually going to look like this. So this is an expansion. Sorry, no, this is a compression. So even I get mixed up. So you're wondering why you get confused. I get confused sometimes, and I've taught this for like 5 years. So don't be too hard on yourselves. This is a compression in X. So we're compressing it horizontally towards, kind of pushing it in towards the center from what we started with. And when we stretch it out like this, you can see that it looks pretty similar to my other examples. I've just reversed what we're doing. This is an expansion in X. Okay, so scale factors between 0 and 1 will expand or kind of stretch it out, and scale factors bigger than 1 will compress. And one of the ways I think about it is the compression in X is sort of like speeding up what's happening to the function. So the bigger the number you multiply X by, the more you've sped up how fast the function is happening. And those are your examples for now. So let's just look at a couple sorts of problems you might have to do. Generally, your problems with transformations are going to ask you to graph a function by taking the base function and then applying transformations to it. And then you have a lovely transformed function. You may also be asked to describe transformations in words, and you may be asked to look at a graph and write down the equation based on recognizing the base function and then being able to use the way that it has been transformed to come up with the numbers that will go in your equation. So let's look at a couple examples. So first example, we are going to graph y equals radical x minus 4 plus 3. So when you're asked to graph something, sometimes we know what our base function is. So our base function here is y equals radical x. And y equals radical x looks like this. And if I have to find some points, I can absolutely find some points. So I know this point right here is 1, 1. My next whole number point is 2, 4. And we can keep going that way, 4, 2. And we can keep going that way if we need to. So what I'm going to do is I'm going to look here. This minus 4 says move 4 to the right because we have it's inside our equation and it's subtracted. So that's going to move us 4 to the right. And the plus 3 says move 3 up. The only transformations we have here are translations. So what I'm going to do is I'm going to take all of the points on my graph and I'm going to use that transformation to shift them. So I know if I have to move 4 right, I'm going to go 1, 2, 3, 4. My starting place is now at 4, and I have to go 3 up. So I'm going to move that 1, 2, 3. So notice what I'm doing is I'm starting by moving a key point. So my key point is that starting point right there. That is my key point. And then I'm going to graph from here the same way I would have graphed this. So I'm going to go over 1, up 1. That was my first point. This point was at 1, 1. Now it's at 5, 4. So now I'm going to go over here, draw that in. My next point would be over 3 and up 1 because that's where I would have found the next point on my graph here, over 3, up 1. So I'm using kind of the same counting scale to get there. So over 3, up 1, and then I have my graph right here. So we have a new starting point of 4, 3 because I've moved it 4 right and 3 up, and every other point also moves 4 right and 3 up, and you can do it point by point if you want. Okay, so what else might I have to do? So example 2, I might have to graph given f of x, and I have a graph here of f of x. So let's see, this is at 1. And then I have a graph that's kind of coming down like a line and over here. I want to graph f of minus x, and I want to graph 2f of x. So if I want to graph f of minus x, so this is a reflection in the y-axis or the x direction. So I'm going to take the same function and I'm just going to reflect it over the y-axis. Okay, so reflect in y-axis. And if I want to do 2 times f of x, well, what I'm going to do is every y value I have is going to get multiplied by 2. So if I was here, I'm going to be up here. And this whole line that I started with, I'm actually graphing from the original function, is going to be up here. And then every point, if I was going to get this, if say I was going over 1 and up 1 to get that point, I would go over 1 and up 2 instead. So that's going to have the effect of making that steeper. And interestingly enough, if you think about a line as a transformation of a basic line, y equals x, your slope is actually your scale factor. So that's kind of an interesting way to think about scale factor, is it takes lines and actually just gives them their slope.